So we are going to look at the concepts of signals and systems right now. So you would have already learned about the subject signals and systems in your previous semester. And we can see that all the physical entities in our day-to-day life, it can resemble a signal and system. So basically you will have something as an input signal which is given into a system from which you will be getting an output system. So let us look at few examples. Like imagine you have an audio system at your home or an amplifier. Now this amplifier is a system and it will accept a audio signal as its input and it will give out an amplified signal, audio signal as its output. So this is a system that is guided by a parameter called gain. So like you typically know that amplifier, it amplifies a signal, and if it offers a gain of X, and if T is a signal over here, then the output signal will be XT, gain times the output signal. You use various softwares for editing your photos or pictures like Photoshop or PixArt in your phone, or you might be using Instagram as well. So all those can be also considered as system. So imagine you are trying to post a picture in Instagram and you have a ready image as your input and you're giving it to one of the filters in your Instagram, and it will give out a modified image. So again, this filter can be treated as a system which modifies the existing image and gives you the corresponding output depending on what the system property is. Sometimes the filter can be for a monochrome image, sometimes the filter can be for a multicolor image, and all that filter is working is like a system, and it will modify your image to give out a modified image to satisfy you. So everything in your day-to-day life can be compared to a signal and system model, and this is what we are going to deal with in this particular subject, learning the basics of it. So when you give a input to a certain system, like over here, your audio, even though from our times, maybe from our age in the 80s or 90s, we mostly had audio tapes, which were analog storing devices. And now you have various devices that store audio in the form of digital information, like your pen drives or hard disk or your streaming services. They all store information as your digital information. And image, as you know, when you open it in a computer, even if you open it via any app, it gives you the image in spatial domain. But as you all know, the image can be in bits, and therefore your image has a certain size that is specified in KB or MB. So images tend to be digital information. So my whole point that I wanted to convey is you have lots of information in the form of analog, and you have lots of signals in the form of digital form, which can be processed to your need. For example, a speech that is overheard in an auditorium. Just imagine what is the scenario. So over here you have the person who is using a mic. You tend to produce an audio signal, and basically it will be transferred to a system. Now this system, like it can have an amplifier which would be modifying the signal, which will be amplifying the signal to a greater strength. First of all, if you look over here, you have a audio signal that is coming out, and then the mic, it does convert it to an electrical signal. So the electrical signal will be passing through the wires and will be reaching the system. It will be amplified, it will be modified as to suit the various needs. It will be processed, and then it will go back as an electrical signal to speakers, and from there you hear the audio sound. So lot of real life situations in our day-to-day life contain a combination of signals and systems, which could really depend on analog as well as digital signals that are part of our day-to-day life. Moving on, we'll be learning about two kinds of signals that we are using in our day-to-day life. One is your continuous signal and other is discrete signal. So for our understanding of this subject, we need to have a concept about continuous and discrete signal. So what is a continuous signal? You have a particular signal which can be designated in the form of x and y, a graph which can be using like this, and you have a continuous signal in the form like this. Now a signal will be called continuous if a value exists for y at every instant of x. Now if you look at this graph, for every value of x you have a corresponding value for y. Now that is how you can define a continuous signal. When you look at a discrete signal, again if you write it as x and y, you will have your signals or the values of y only at certain points of x. So if values of y exist only at certain points of x, then it will be known as discrete. So this can be for explanation for a continuous signal, and this can be an explanation for a discrete signal. Now when we look at it in this perspective, I have just mentioned it in the terms of x as well as y. Now based on what you have learned in your signals and systems, you mostly have used a graph where you have x of t as one parameter defining x. Correspondingly you will have x of t. Now this would basically mean a continuous time signal. What I explained previously was the two forms of signal, but when we specifically give a value for x and its corresponding y, it could become a continuous time signal, or in terms of frequency we usually write it as omega and we write it as x of omega, which will make it continuous frequency signal. And obviously you would have signals that are of discrete type also. So mostly in z domain you would be representing it in x of z. That would basically a discrete z domain signal. So that basically covers up the explanation for a continuous and discrete signal. I hope the concept is clear. My point was I wanted to convey what is the difference between a continuous signal and a discrete signal if it is for a corresponding y as well as x. Now when x and y takes definite cases, like in this equation over here you have t representing time, the corresponding y becomes x of t. So this becomes a continuous time signal and this becomes a continuous frequency signal, while in z domain it mostly is in discrete form, so it will be discrete z domain signal. Moving on, we will learn about a conversion of a continuous to discrete signal, and in that process we have to learn about sampling, quantization and digitization, which are the three processes that would be involved in conversion of a analog signal to digital signal. But let me talk or say that the concept of analog and digital is different and continuous and discrete is different. So let's keep that in mind, but some way it goes hand in hand, and let's see what happens. So let us assume we have a continuous signal and it is shown in the graph that is being drawn over here. So I'm drawing a pretty big graph, and this is my time graph and this is my x of t. So I'm having a message signal over here, a sort of sine wave, as you can see over here. So this is my message signal. Let's assume this is my message signal. Now I am drawing a concept of sampling signal. Now typically sampling signals shall be spaced apart in a uniform way. Typically they are of the same height as well as same interval. normally for a uniform sampling process. So I repeat what I say, the time span between these two and these two will be same, and I'm assuming that they are having the same amplitude as shown over here. Let that be 1. Now, how do we obtain the sampled signal? We have the message signal over here and we have the sampling signal. It can be treated as analogous to a multiplication process that happens between these two signals. So when x of t correspondingly gets multiplied to this one, we get a corresponding sample. So if you look over here, that means if we are sampling the signal, the sample signal will be containing values only where the samples exist. So we are drawing these broken lines. So when the sample x of t's value is 0 over here, 0 into 1 typically is 0. So this is the sample that we are drawing. And then when it comes, let us assume this corresponds to the peak. So this is the sample at this point. And when we have, let this be the, and just like that, we have obtained all these samples that we are supposed to obtain from all these corresponding points of the reference of the message signal and the sampling signal. Now you can see here that this is a sampled one. Now you have learned about the sampling theorem, which states that fs shall be greater than or equal to 2fm, where fs is a sampling frequency and fm is the highest component in the message signal. So typically what it means that if you want for proper reconstruction of the signal, the sampling frequency shall be greater than twice the highest component of the message signal. So that condition is obeyed over here. Now when we connect these dots, we can see that we are getting a wave that is similar to the sine wave. Even if I cannot say that it is comparatively original, similar to the original signal, we can see that this approximation is almost similar to that particular message signal. Now this sampling process would have been more effective if the number of samples would have been increased in this span of duration, which is simply what is meant by this sampling theorem, or what you have learned previously in your previous subject. So then once this happens, you will have to undergo a process of quantization. Quantization basically refers, if this is a sample of 0 to 5 volt peak to peak and minus 5 over here. Suppose if you get a sample over here 0, this is 3.6, this is minus 1.25, and so and so. So quantization basically refers to the fact that you cannot convert every value that you obtain in the former sample to its original to its exact binary format. So what we do is 3.6 will be rounded off to 4, minus 1.25 will be rounded off to minus 1, and these values will be digitized to suit our to store our information into binary format. Now these values obtained by sampling will not be used, but rather the quantized versions will be used, and these values will be digitized. For example, when our signal is from 5 to minus 5 volt, we should expect how many bits for storing these values. For storing a maximum value of 5, we need 3 bits. 101 is the exact binary for 5, and 1011 again for the minus 5. But then how do you differentiate between these two? You need a sign bit. So let us assume 0 is used here and 1 is used here. So 0101 will be representing 5 and 1101 will be representing minus 5. So with this the digitized concepts can be implemented. So a value like 4, it will be stored as 0100, like a negative 1 will be stored as 1001. So we just explained the concepts of three concepts basically. Signals and systems model was explained. Then we learned about continuous and discrete signal. Then we learned about sampling, quantization, digitization, overall covering up the topics of how to convert a continuous signal to a discrete signal. And that is with the help of the sampling process. So we'll move on to the next topic. Thank you.